As you can see, I'm back to doing a longer video here now. It's also going to be a harder video, but these things really are a labor of love for me. I want to help you understand challenging, difficult things to help you be successful, both in math and maybe as an actuary. So I hope you can stick with this and understand as much as you can from it. I think it is definitely worthwhile, but you may need to pause it and take a break if you need to here. We're going to be looking at problem 5.3.1, part B, a modified version of it. I've added some extra directions from Broverman. It's kind of hard to describe in a short sentence here. I'm describing it as an approximation, and you could also say understanding the approximation, to what you could call a dollar-weighted yield of a fund over a single year. So we are doing it over a single year, and we are going to use simple interest because of that, whose benefits and interest are paid continuously at a uniform rate, which is a bit strange for the interest. That's sort of saying we are assuming simple interest, but whose single contribution beyond the initial balance is a lump sum. Right, so it is a long, hard problem. We may even need another piece of paper as we go through this. Let's see if we can fit it on one piece of paper or not. So you've got a situation where you've got a bunch of workers contributing to a pension fund. You've got a large pension fund holding money that is going to pay benefits to these workers when they retire. It's got a large value of $500 million at the start of the year. Okay, because you've got a lot of workers both contributing to the fund and taking money back out of the fund, it's not too bad a model to assume things are happening continuously. Every month, every day, every hour, every minute, maybe even every second of every day, money is going in and out. And you can approximate how fast it's going in and out, maybe in simple ways. And that's what we are going to do here. During the year, the fund receives contributions of $100 million. So that would be money going into the fund from the company that has these workers and has this pension fund set up for them, pays out benefits to retirees of $40 million. So that's money coming out of the account, and does grow in interest, has interest income of $60 million. The goal is to estimate the yield rate I, and you could call it then a dollar-weighted or money-weighted yield rate because it's going to be assuming simple interest for a year. In the following circumstances, the benefits and interest, benefits meaning money coming out of the account to the retirees, interest meaning the money is growing in the account, are uniformly spread throughout the year. And again, that may not be realistic, especially over a long time period, but maybe over a short time period, it's not too bad. But the contributions, and in fact, it's only going to be one contribution in each of these situations, is made in one lump sum at different times. 0, 1/4, 1/2, 3/4, 1. So there are going to be 5 answers to this question. I will say that I like to do this by coming up with a general formula for what the yield rate would be at an arbitrary time for this one lump sum contribution, and then use that formula to quickly find the answers for these 5 parts. Okay, that'll be more efficient. Okay, and I would be illustrating how to be efficient on this kind of problem. Adding some extra directions, this first bit actually is something, if you're using Broverman's book, you should find out by reading the text, because I'm just saying make sure you find I by an approximation from the text given by this formula here. It's kind of a mysterious formula. You've got, well, capital I is not too mysterious. That's the total interest, which is $60 million. But you're integrating a function here. What is this function? Capital F of t is the fund balance at time t. That's kind of strange. Why would we integrate the fund balance? Usually you integrate a rate of change or something, but this is the actual balance. It's kind of a strange thing here. And we are assuming, to make things as simple as possible, that capital F of t has a constant rate of growth or slope. However, I should say right at the outset that because we're having these lump sum contributions, that $100 million is going to occur at one spot in time during the year, capital F of t is actually going to be a piecewise function, piecewise linear, with a constant slope for each piece, but it's not going to be continuous. It's going to be discontinuous. There's going to be a jump discontinuity in it, and that's what makes this formula necessary to be more accurate, you might say. But it is kind of a mysterious formula. However, at the end of the video, I also, and this is the hardest part, want to give a justification for this formula in this situation where we're assuming simple interest and we're assuming this continuous growth. the continuous rate at which the contributions, benefits, and interest are being paid. All right, that's a lot to think about. Before I get into more details, I just want to also show you my motivation for talking about the justification part of this. So we're looking at Broverman's book here, the 7th edition of the Mathematics of Investment and Credit. This is page 318. Essentially on pages 317 through 318 up to this point, they derive this approximation for the yield rate. And then after that, they say it is possible to generalize this equation here, 5.8, to a new equation, 5.9, that is the same as the equation I just showed you on the piece of paper, involving the integral of capital F of t, though they do it over an arbitrary interval from t1 to t2 instead of from 0 to 1 like I showed you. Now, it's not too hard to see that these formulas give approximately the same answer if the interval from t1 to t2 is fairly small, and if capital F of t is not too wildly behaving, you know, it's maybe a straight line or maybe a parabola that's got just a small amount of curvature to it. These, if you use the trapezoid rule to approximate that integral, it's pretty easy to see that these are approximately the same, though they could be fairly far away from each other if the interval's bigger, or if capital F of t is a little bit more wild in its behavior. Maybe, you know, what if capital F of t is piecewise continuous, like they mentioned down here, and like our problem is all about, actually. It's maybe better to use this formula. And maybe it's going to give us something that's not super close to this formula. So the real issue would be, where does this formula come from? The text just says it's possible to generalize this equation. But it's not real clear to me, besides saying these are approximately equal over small intervals and well-behaved capital F of t, why you would do this. Okay, why you would integrate capital F of t. And I was reading the derivation and it wasn't clear to me why you would think about it this way. So what I want to do again in the last part of the video is I want to justify the formula in the example we're considering when I generalize these numbers, essentially. How to think about why that formula still makes sense that you see right here. Okay, at least for this example. So I hope you can stick with this video to that point. All right, but let's do the main part of the problem first, where we get these answers here. And I think it would be helpful to draw a graph first of the fund balance, since we're going to have to integrate it. So we've got the time here, t, in years. Here's time 1. And this vertical axis would be fund balance in millions of dollars or whatever. You could pretend it's euros, whatever you want. It starts out with a balance of 500 million. By the end, what is the balance going to be? Well, you're receiving contributions of 100 million. Pays out benefits of 40 million, so the net contributions are 100 minus 40 is 60. But then there's also the interest income of 60 million, so 60 plus 60 is 120. 500 plus 120 is 620. By the end of the year, we're going to be up to 620 million. So the graph starts out right there and ends right about here. And the graph, because of the assumption of constant rate of growth, is going to have a constant slope. However, there's going to be this jump discontinuity. There's going to be this some moment in time, capital T, just pretend it's right here, for example, where you have a jump in the fund because of that one lump sum contribution of 100 million. So, you know, if this were 510 million at this moment in time, you would jump up to 610 million up to here. Should I put an open circle here and a closed circle there? It really doesn't matter. You could do it either way. I won't even bother drawing an open or closed circle. And the fund's going to grow after that point up to the 620 million. And notice that I'm assuming linear growth here to keep things simple. Okay, of course, in real life, the interest would not give you linear growth. We're going to assume simple interest to make this problem as simple as possible. This gap right here is 100 million. What is the slope of each of these pieces? These pieces are going to have the same slope, in fact. And if you think about it in terms of the interest that is coming into the account and the benefits that are paid out, 60 million total comes in from interest, 40 million in benefits coming out. That means 60 minus 40, 20 million over the year is the net increase from interest minus benefits paid out. This slope in both of these pieces should be 20 million over 1 year, 20 million per year. Okay, and that's going to help us figure out the piecewise formula for capital F of t. This is capital F of t here, which we are going to integrate. We need a piecewise formula for it. The slope is 20, so I can say capital F of t is 20t plus something in each case. In this first case, for little t between 0 and capital T. And in the second case, little t is between capital T and 1. I'm making that a less than or equal to and that a less than in an arbitrary way. I could have made this a less than and this a less than or equal to. It doesn't matter. You can see the vertical intercept here for the first piece is 500, so this would be plus 500. The vertical intercept for this one, well, you don't need to really think about it because you can just think about the fact that we have a jump discontinuity of 100 here, so we have to add 500 plus 100. We have to add 600 for the second piece of the formula. All right, now we're ready to integrate this thing to get this part of the formula here. Integrate capital F of t from 0 to 1. Well, it's a piecewise function. I could integrate it from 0 to t, and then add the integral from t to 1. However, these formulas are almost the same, so you could think of it as the integral of the pieces that are the same, 20t plus 500 really, is the same in both pieces, plus the integral from t to 1 of the part that's not the same, the extra 100 that comes from the jump discontinuity. Okay, so I hope you see what I did there. I could have integrated from 0 to capital T, this thing, then added the integral of this thing from capital T to 1. However, these formulas are almost the same. I could think of this one as this formula plus 100, so I could really integrate the original formula from 0 to 1 and then the extra from capital T to 1. So we'll get, when we do the integral, we'll get 10t squared plus 500t going from 0 to 1. And then this one we're integrating a constant. That's going to be the constant times the length of the interval, 100 times 1 minus capital T. Plug in t equals 1 here, you get 510. Plug in 0, you get 0. You get 510 here plus 100 there minus 100t. This simplifies to 610 minus 100t. That is what that integral equals in the general case. Let's go ahead and simplify the formula for I now in the general case, and then we can find the answers very quickly once we have that formula. So you could write I, you could maybe even call it I sub capital T for the different capital T's. Looking at this formula, it's 2I, where capital I is the total interest earned, which is 60. 2 times 60 is 120, 120. Over 2 times the integral, 2 times this thing. It's going to be 1220 minus 200 capital T, and then minus capital I is going to be minus 60. And we can simplify this if we like, 120 over 1160 minus 200t. Then we could divide everything by what? We could divide it by 10 and get 12 over 116 minus 20t. We could then divide everything by, they're all divisible by 4, aren't they? So we could write this as 3 over 116 divided by 4 would be 29, and 20 divided by 4 would be 5. So we could simplify to this. You can use any one of these formulas here to get your answers. And now let's go ahead and get the answers. Now, it's a little confusing. You might wonder, when t is 0 or t is 1, is there really a jump discontinuity? Well, yeah, kind of. I mean, you would sort of imagine in the t equals 0 case that you'd have just the 500 point here, and then it would jump immediately up to 600. Maybe you'd have an open circle there at 600 before continuing on. But anyway, you can think of it that way in any of those cases. So we'd have I sub 0 being 3/29. Go ahead and use the calculator. 3 divided by 29 is approximately 0.1034. I sub 0.25 for t equals 1/4. should be a bit bigger, right? Because if the jump is occurring at some later time, your fund was spending more time in lower balances and you got the same amount of interest in the end. So in a sense, the interest should be higher when capital T is higher. Is it here? 3 over 29 minus 5 times 0.25. 0.25 times 5 is that. Subtract that from 29. Take the reciprocal of that times 3, get about 0.1801. Let me just say the answers for the other ones instead of spending time with the calculator so we can get to some other stuff here. This also part up here is what I want to get to. I of 0.5 turns out to be, I'll just tell you, 0.1132. You should check these on your own. I 0.75 turns out to be about 0.1188. And I of 1, excuse me, where the lump sum is at time 1 turns out to be about 0.125. Okay, so again, as the lump sum gets later in the year, the total yield rate I gets higher because that should make sense again because you're spending more time in lower balances yet still getting the same amount of interest in the end. Okay, so now we're to the extra hard part, as if that wasn't hard enough as it was here. So what I want to do now for this last justification part is I want to justify where this formula comes from and especially where that integral comes from. And I'd like to do it in an even more general setting. It's still going to be piecewise linear function here for capital F of t, but I'd like to use more arbitrary symbols here. Let's label the starting balance capital F sub 0. After all, it does equal capital F of 0. And the ending balance capital F sub 1. The total interest we will label as capital I. Total interest, but you could also think of that as a total interest rate at which interest is being earned, if you like, because we are assuming uniform over 1 year. B is going to represent the benefits paid to the retirees, which will be in this example is the 40 million. But once again, you could think of it, since it's over 1 year, you could think of it either as a total amount of benefits or a rate of benefits in millions per year, for example. And to be consistent with Broverman's notation, I'm going to call this jump discontinuity, this net contribution at time capital T, I'm going to call it C sub capital T. Okay? So I'd like to come up with this derivation of this formula based on these symbols, and I am also going to assume piecewise linear. But what we need really to get the derivation here is we need to think about an equation of value based on assuming simple interest. And I'm also going to assume one more thing. I'm going to assume the benefits are paid actually in one lump sum, even though they're not. And you might wonder then, when would that lump sum be paid? It's going to be best to assume it's paid halfway through the year. Okay? We can justify that in a few different ways. And in fact, if you look at Broverman's derivation of the simpler formula, that's an assumption that could come from essentially using the trapezoid rule to do an integral approximation. But we don't have to think of it in terms of integrals. So what is the equation of value? The ending balance, f sub 1, which really is the same as f of 1, would be the initial balance, f sub 0, at time 0, promoted in time forward by 1 year, so multiplied by 1 plus I. Then we've got the contribution at time t, C sub capital T, going forward in time 1 minus capital T years. Now again, I could try to be more accurate here and assume compound interest, but I'm going to assume simple interest, so I'm going to multiply this by 1 plus I times that amount of time, 1 minus capital T. And then I have the benefits paid out. Now again, technically the benefits are paid out at rate B, $1 million per year, say, And so I could really multiply this by like a future value of a continuously paid annuity. However, to keep things simple, I'm going to assume simple interest. I'm going to assume the benefit is actually paid out of one lump sum halfway through the year. So I'm going to multiply it by 1 plus 1/2 times I. Okay, we're just trying to get an intuitive idea for things, so we're not really being as accurate as we could be. You might say this is an approximate equation rather than an exact equation. You could think of it that way. All right, let's go ahead and simplify this, the right-hand side here, and then let's solve for I. So I can figure out the terms that don't involve I first. There would be an F0. F0 times I does involve an I. With the CT getting distributed through here, it only times the 1 does not involve an I. And with the B here distributed through, I get a minus B right there. So those are the terms that do not involve an I. Then I have plus I times the terms that do involve an I. I've got an F0. I've got a CT times 1 minus T. I could distribute the CT through that. If I like, I could write it as plus CT minus CT times T. Or I could factor the CT out of that and write it as CT times in parentheses 1 minus T. And then I also have a minus 1/2 B. All right, now I can solve this equation for little I. Just subtract this from both sides and then divide both sides by that. So I could write an equation, you might say an approximate equation for little I, as F1 minus this would be F1 minus F0 minus CT plus B, all divided by this thing here. So that's going to be F0 plus CT minus CT times T minus 1/2 B. Okay, so that's one way to write the equation for I, the approximate equation. Kind of complicated looking, but it is one way that you could think of it. By the way, this quantity up here, if you think about it, would be the same as I believe. Let me think about this here. You've got the ending balance minus the beginning balance. That would be what I plus contributions minus benefits would be. So if you subtract the contributions and you add the benefits, this would be the same as I. Okay, that is the same as I here. What do I want to do next? Now I want to think about the integral here. And based on this assumption that we've got a piecewise linear function, let's go ahead and figure out what the integral is. Figure out what this formula is, simplify it, see if it simplifies to the same thing or not. Okay? So this is not maybe the most satisfying derivation because we are making so many simplifying assumptions, but I still think it's worthwhile doing, and I hope you do as well, just to confirm that the formula is giving you what you would get if you thought about this in terms of an equation of value based on simple interest, just like we do with these dollar-weighted rates of return and money-weighted rate of return. So what's the general formula for capital F of t as a piecewise formula? Essentially, I'm going to generalize what I did up here. The slope is going to be constant. And the starting value, that's the F0 there. So over the initial time interval, I've got the starting value F0 plus what is the slope going to be based on the notation I have here with the I and the B. It's really I minus B, that is the net amount going into the account, excluding the lump sum. And you could think of that as a rate of change as well, because you were doing it over 1 year. We could think of this formula as F0 plus I minus B times little t, where little t goes from 0 to capital T. And then for the second piece, I just add the lump sum contribution, the C sub t, to that. So I'd have F0 plus C sub t plus also I minus B times little t. Now little t goes from capital T to 1. So essentially we're doing the same kind of thing we did up here, except in a general case. And again, we are matching it with the way we think about it in terms of an equation of value and seeing that we get the same thing. So again, I think it is still worthwhile. So what is the integral of this going to be? Just like we did before, we could integrate from 0 to capital T and then add the integral from capital T to 1. But again, these formulas are exactly the same except in the second piece you add that extra c plus c sub t. So the integral from 0 to 1 of the whole function could be thought of as an integral from 0 to 1 of the initial piece, f0 plus I minus b times t from 0 to 1, and then add on the integral from capital T to 1 of just that extra piece there, c sub t. Okay, and that'll be c sub t then times the length of the interval, which is 1 minus t. But here we actually have to do the integral, although with f0, when we integrate from 0 to 1, we'll just get f0. I just go ahead and write that down right away. Then we have the piece that involves the t there. When we integrate it, we'll get a t squared over 2. So I have I minus b over 2 t squared, t going from 0 to 1. And again, this thing is c sub t times 1 minus capital T. Plug in 1 here, you get t1 squared is 1. 0, you get 0 squared is 0. So we have f0 plus, well, let's write it as 1/2 I minus 1/2 b plus ct times 1 minus capital T. And what am I trying to do? I'm trying to go back up to this approximation now, which, by the way, I think I'm going to divide the top and bottom by 2. Certainly I can do that. Based on that approximation, I could say I is approximately capital I divided by the integral minus 1/2 capital I. I just divided everything by 2. What will that simplify to here? Capital I on the top, which does match a capital I on the top there. So if the bottom simplifies to this thing, we'll be done. Well, let's hope it does. Okay, so what do I have here? Actually, we can just look at these things to do it. This is the integral right there. So that goes right here. But then I have a minus 1/2 I. The minus 1/2 i's will cancel. So in the end, do I get a match? I have a capital I on top. I've got the f0. That matches that f0. I've got the ct times 1 minus t, which is the same as that. Same as ct minus ct times t. And then I have a minus 1/2 b. Yay, this worked. Okay. So I hope that was satisfying to you to see that we have, in the end, this matching this whole thing. And this was an I up there. To see that this formula can be made sense of, at least in this special case, and making simplifying assumptions. For a more general derivation of the formula in the book, I'm going to continue searching, and you could search as well. Broverman's book doesn't have it. I looked in another book, it didn't have it either. I looked online a bit, I couldn't find a derivation, but maybe we'll find one eventually here.